Okay, welcome to our series of understanding Higgs mechanism. Today we are digressing from our main topic because the digression means because we want this what we are going to work today that will be required later. So we are Maxwell's field tensor. We are discussing Maxwell's field tensor. This field tensor we will require in our main topic. So today we are discussing Maxwell's field tensor. Maxwell's equations, everyone knows that the Maxwell's equation is the four Maxwell's equation of electric and magnetic fields. Divergence B is 0. Divergence of B is 4 pi rho. Curl of H is 4 pi by C J plus I by C delta D. This everyone knows, but just to recall, I am writing on the board. Minus 1 by C dV by dt. And D, this decimal current is epsilon times permittivity times the electric field. B is mu times H and J is sigma times E, is called Ohm's law. So all these things we know. Now we want to express these four equations of Maxwell's in two equations in terms of, we will express Maxwell's equation in terms of scalar field and a vector field. So the first one, that is, we have divergence of B is 0. We know that the curl of a divergence is 0. It means we can assume B to be the curl of any vector field. So we can write that B is curl of a vector field A. Because if we substitute here, it will be divergence of curl of A. And we know that the divergence of a curl is 0. So satisfied. So it means B can be expressed in terms of a vector field A, which is the curl of which gives you the magnetic field value B. Now this equation, substitute the value of B here, you will get this one, curl of E as 1 by C dV by dt. This is the fourth Maxwell's equation. It's also called Faraday's law of electromagnetic induction. So it is minus here, minus 1 by C d by dt. And for B we have written curl of A. So it is curl of, take everything the left hand side. So it's curl of E plus 1 by C d by dt, curl of A is equal to 0, which can also be written as E plus 1 by C d A by dt. So this is another, say, a vector. So it's a curl of a vector. It means the curl of a vector, this can be expressed, this vector can be expressed as a gradient of a scalar field, because we know that the curl of a gradient is 0. So this bracketed term can be expressed as E plus 1 by C dA by dt. This vector can be expressed as a gradient of some scalar field, say phi. So it means E can be expressed as minus del phi minus 1 by C okay. So it means phi is say we can write it like this, a 0 and this is minus 1 by C. So we have expressed B in terms of the vector field A and E in terms of a scalar field phi and a vector field A. So both E and B, electric field and magnetic field, is represented by two field, one scalar field and another vector field, where phi can be written as in 4 dimensions. This is the time part, or this can be written as A naught A. So now this whole equation, okay, so we have it at our disposal. B is equal to curl of A and E is equal to minus 1 by C del phi. Oh, sorry, it's not here. It's minus 1 by C here. 1 by C. The electric field and magnetic fields. Now the electric magnetic field tensor, electric field E and the magnetic field B can be represented in terms of tensor. In tensor form. This can be written as F mu. This is A mu x mu minus that A mu that x mu. Where A mu runs, mu and nu runs, it's indices, the value of which is start from 0, 1, 2, 3. 0 corresponds to time component, and for x component, y component, and z components. So it's in 4 dimensional we can write in terms of indices, and a mu, which is the covariant, it's written as phi minus. This has 3 components. This does time component a naught. This can be written as phi or a naught. This is ax, ay, az, a1, a2. Now this is the contravariant component written as phi, and this is the difference of plus minus 0. Now the gradient term del v is del by del x naught, del by del t. Suppose this is del x naught is ct, c is the speed of light, and this is the 3-dimensional del. This is the 4-dimensional. So covariant terms of this will be written as del by del x naught. So these we will use here. So this is our electric field magnetic field tensor. Electric field magnetic field can be written in tensor form like this. Now substitute, suppose we have taken mu as, now we have 4 components, 0, 1, 2, 3. So suppose we take mu as 0 and nu as 1. So it will be F01. F01 is del A1 by del x minus del A0 by del x1. Del A1, which means this is x component of del AX. Del A, so it will minus, so it is minus, and this will be C del x naught is C dt minus del A naught. A naught is 5 count. So the A naught is 5. This is A naught, this is A1, A2, A3. So it is del 5, and this is del x. So this is nothing but okay. This is the x component of the electric field here. Del 5 by del x minus 1 by c del x by dt. So this is the F01 is x component. Okay. Now similarly, suppose suppose mu as 3 and nu as 2. So it will be F32 minus del A2 by del x3 minus del A3 by del x2. A2 is y component. So the A2 will be, this is A1, A2, A3, A naught. A naught is the time component, this is phi. So it is A2. A2 means minus del AY, del x3, del by del x3. Del by del x3 means z component, del by del z. Minus del A3. Del A3 will be del Az by del Y. So it is this is the x component. X component of this will take the curl of the x component will be del Az by del Y. So in this way we can find the whole the matrix of, so the whole matrix will be like this. F00, it will give you 0. This is 0. This we have found out as Ex, and this will be Ey. If you work out, this will be Ey, and this will be Ez. This is minus Ex minus Ey minus Ez. Diagonal will be, all the diagonals will be 0. That is, this will be minus Bz By. 3, 2 we have already worked out. 3, 2 is this much. 3, 2, this. It is Bx. This will be Bz. This will be minus By. Obviously this will be Bx. So this is the tensor. Now if you take the contravariant component, this sign will change. This will be plus, this will be minus. If you take the contravariant, the contravariant component, this will not change, only the electric field component will, the sign of electric field component will change. Ex minus Ey minus Ez, Ex Ey Ez 0 minus Ez Dy 0 here. Bz 0 minus Bx minus By Bx. So these are the Masroor's field tensors which we will require in the further, to go on further. Some more. I can give this here. The Lagrange for the Masroor's field equation, electromagnetic field. Lagrangian for electromagnetic field, that is written as 1 by 4 pi f mu f mu. This we know what is this f mu f mu. This represents electric field and magnetic fields components, and plus the current part G mu by C A O. Actually this is 1 by 4 pi, and this is delta A mu by delta x mu minus delta A mu by delta x mu. This, similarly this will be, this is contravariant covariant, and this is A mu So this is delta A nu by plus 1 J mu by C. Mu and nu runs from 0 to 1, 2, 3. Okay. So this is our Lagrangian quadratic field. Now we have the Euler's. If you substitute this into the Euler's Lagrange equation, you will get the Maxwell's equation. So it's okay. I will do it. It's not required here, but still I will do for continuity. So Euler's Lagrange equation. We know that we have Euler's Lagrange equation. This is del by del x nu. Minus so this is our Euler's Lagrange equation. Substitute this. So if you substitute, first calculate this one. So it will be delta L by delta A mu delta x. If so, differentiate this with respect to del A mu del x mu, it is this will be you will get 1 by 4 pi this is 0. This is del A mu by del x mu. It will become 1, and this will remain as it is. So it is del A mu by it means you obtained minus 1 by 4 pi this value. This you obtained. Now this we have problem. Now we differentiate again del by del x. So differentiation of this. Now on this side del A by del L by del A mu. So del L by del mu means this one is differentiated. This will give you J mu by C only. So if you substitute these values here in this Lagrange equation of motion, you will get the derivative of this is del by del x mu of minus 1 by 4 pi del A mu by del x mu minus del A mu by del x mu, and minus that del L by del A mu part. This will give you J by C. So it will give you J mu by C. So this is substituting on the left this equation, we get this. Or you can write this as this is nothing but electromagnetic field tensor. So it is del by del x nu F mu is equal to 4 pi by C J mu. This is our Maxwell's equation in tensors form. This is we do not require these things. We are interested only by Maxwell's field tensors. What is the Maxwell's field tensors? F mu nu, and this is this same type of equation we will write. We require, so it's not. I have just completed the whole thing, just to complete the subject, but we require only that part. Tensor, Maxwell's field. What is Maxwell's field tensor, and how it is written. Now, come to our discussion on the Higgs field. We are discussing about the Higgs, and we have discussed that the Lagrangian is a difference of kinetic energy and potential energy, and in terms of in one-dimensional motion, classical one-dimensional motion, the Lagrangian is kinetic energy minus potential energy. And kinetic energy is, say, half mv square, is the variation of position with time, square of the position with time. And the potential energy is, if you take the case of spring, it's a half kx square. X is also, it's the variation with, this is actually half mx dot square, this is x square. So the kinetic energy depends on the variation of the position with time, and the potential energy depends upon the variation, square of the variation of positions. In field, we have field values varies both with space and time. So it will be square of the variation of both space and time. So since potential energy for the field is proportional to phi square, as x square is a phi field values, and the kinetic energy will be the variation of field with space and time. So it will be d phi by del x mu and del phi by del x mu is the square. We have discussed that this is a contravariant and covariant, and this this can be written on, had this been if this been the scalar quantity, the contravariant and covariant will be no difference, but if it's a vector quantity, we have to write it like this. So the Lagrangian is a difference of kinetic energy and potential energy. So the kinetic Lagrangian for a field value phi, suppose we take one of the fields, say phi, if the kinetic energy is equal to half del phi by del x mu del phi by del x. This is the kinetic energy part. Because mu is here, contains both space and time part. This is time component, space component. So it's variation of field with both space and time. Del phi by del x0 means it's variation with time. Del phi by del x1, that's the variation with along x-axis. That d phi by dx2 will be along y, and so on. So it is minus the potential energy. So it's the potential energy means half, say it is m c square by h, and it's phi square. Phi is square potential energy. And this is just like here. So this is some parameter. Then m is the mass, and c the speed of light, h is the Planck's constant. So this can be written as 1 by 2 del phi by del x mu del phi by del x mu minus 1 by 2 mu square phi square. This bracketed term is written as mu square. Now again substitute this in Euler's Lagrange equation. This is the Lagrangian. If you substitute in Lagrange equation of motion, you will get the equation of motion. So we have the Lagrange equation of motion, del mu del by del mu, okay, that this is del L del minus so this is our Euler's Lagrange equation. Equation of motion. Substitute the values of this. First differentiate this Lagrangian with respect to del phi by x mu. If you differentiate this, when it means differentiating with respect to this, you will get first part or this one, then so it will be delta L by variation of this, differentiation of this with respect to del this quantity. So we will get 1 by 2 del phi by del x mu. The 2 will finish. Now worked out this one. Del by del mu means okay. Del mu is del by del x mu. So this will give you this will be nothing but del phi by del x mu square. You can take now if you differentiate this with respect to del phi, you will get minus mu square phi. So if you substitute this here, you will get del square phi by del x mu whole square. Oh. And minus minus makes here minus makes plus will be mu square phi. So this is our equation of motion. This equation of motion is similar to that of particles attached to a spring. The equation of motion for the particles attached to a string will be d square x by dt square plus omega square x is equal to 0. This is just like simple harmonic motion. This is the simple harmonic motion. of the field. This is just like here, this is plan motion. Now the potential energy which was here in this case, in the particle case, what's half is being constant kx square. So the potential energy in this case was half kx square. So if k is the spring constant which is positive, the potential energy varies with this x square, so the potential energy comes out to be like this. Parabolic x here, potential energy here. Now in this case the potential energy is given by this. In the field we have the potential energy is equal to half mu square pi square. In the spring case, the Lagrangian is half m x dot square minus half k x square. It's just like this equation which we have erased. It's a kinetic energy minus potential energy. This is x here, phi square here. This is the potential energy. This is the potential energy here. So if we take mu as positive, if mu as is positive, the variation of potential energy with the field values will follow the same graph, parabolic graph. So it will be here field values, potential energy. It means as the field excites, the excitation of field will produce say a particle excites a particle which will vary here. The particle will vibrate in this parabola as the field values increases. So the kinetic energy will produce the vibration of the field, which will then excites particle, because the field quanta, if the field is excitation, it emits a quanta. That quanta will vary potential energy. Now if mu is 0, it means there is no quanta. Although the field is is having kinetic energy, it's varying, but it has no quanta, which means although if it produces the quanta, it has no mass. But because this has mu is related to n c square by h, it means this has no quanta, although mass. So now if mu is negative, if the mu is negative, it means the potential energy curve will be upside down. The parabola will be upside down, and in this case, the parabola will be field here, potential energy here. It means even if the quanta is created, that cannot stay here because this is unstable equilibrium. This has to fall down either this side or this side. It means it will not rest at them. It cannot vary like this potential curve. So the field, this has a field, it has no mass. It's no mass case. This is positive mass case. And if the field, this is unstable equilibrium, So all these three cases may arise. Either mu will be positive, or mu may be negative, and mu may be 0, or mu may be negative. So we'll see further on these. Further we will discuss these things. Even if mu is taken negative, and okay, then we will see.